Hi everyone. Started. Okay, so today also we'll be discussing two problems and there will be a few homework for you guys. All right, so let's actually start with the first problem, like discussing the first problem. It's a easy problem. So you're asked to print all the nodes of a binary tree that doesn't have sibling. Now you are given a binary tree of size n. Find all the nodes which do not have any sibling. You need to return a list of integers containing all the nodes that doesn't have a sibling in sorted order, right? So you have to return the list in sorted order. And what is that you need the nodes that doesn't have a sibling. What do we mean by sibling? Sibling means if for the parent it has another child node, right? So for this node, let's say 20. 20 has a parent of 37, right? So 37, does 37 has another child node apart from 20? No, right? So 20 does not have a sibling. So that's the definition of sibling, that it the parent will have another child node, right? The parent node will have another child node apart from this node. Now note that you should not return the root node in your answer, because it is always it will never have a sibling, but you have to return the other nodes, right? So in this case, both 20 and 113 doesn't have a sibling. In this case, you have to return -1, because 2 and 3, like 2, for 2 the parent is 1. 1 has another child node, which is similarly for 3, parent is 1 and it has another child node 2, right? So that is the definition of sibling. And we have to do this, like it's pretty simple question. I'm pretty sure that you have already understood how to solve this. So we have to solve it in order of n log n and order of height of tree space complexity. So let's actually quickly understand, like, how do we solve this. It's pretty simple, so I don't want to spend a lot of time around this, but the second question is okay, so is good, so we can spend more time on that, right? So yeah, so what is asked here is now nodes that doesn't have a sibling, right? So let's say 1, 2, 3, 4. How can we know that a node has sibling or not, right? So what we can do here is, for a given node, right? When we start off, so we are doing a DFS. We'll do a DFS or a traversal, or we do a DFS. When we do a DFS, we will also pass the state, like whether it has sibling or whether it doesn't have sibling. So from 1, we will go to 2. But when we go to 2, we'll also check, is there the right child available as well, or is there for the right child, we'll check if the left child is also available. So as it is available, so we'll call DFS2 with false, because it is not a it has a sibling. But from 2, when we go to 3, when we go to 4, sorry, we will call DFS4 with true, because only only child node is 4 and it doesn't have another child node, so we'll call DFS4 with true, right? So we'll have a state, when we do a DFS, we will have a state which uh, is no sibling, or sibling absent, something like that, right? Sibling is not there, sibling absent. So we can have another another variable in our DFS that will be sibling absent, that can be true or false, and we will pass, like, accordingly, if the sibling is absent for a given node or if it is present, right? So we'll store all the nodes in a vector, and finally we have to return in sorted way, so we can just return like sorted and send it, right? So as simple as that. Let's try to write the code for this quickly. Like, it's a pretty simple problem. uh, okay, so we will have a helper method here, void dfs, and we will also have our answer here, right? So vector int answer. And here what we'll do, first thing that we'll do is answer dot clear. We'll first clear the answer, and finally we'll return answer. Now we have the node, right? So this will also take node star node, and bool is sibling absent. Let's maintain this. So if it is absent, so let's write it down. If is sibling absent, then we'll answer dot pushback. We'll add it to the answer. So answer dot pushback node of data. Also, we have to sort it, right? We have to sort it as dot answer dot begin, answer dot end, and we will call here. We'll call DFS with the root node. But for root node, we will run return false, right? We'll keep is sibling available false, because root node we don't want it in the answer, right? So this will be there. Now, if node of left not equals to null, node of right not equals to null, means if both the left and the right child are present, right? So in both, for the left and the right child both has sibling, so we will call DFS node of left, and it will be false. Sibling is available. Sorry, sibling is not absent. Sibling is available, so false. So DFS again node of right, and it will be false again, right? And after that we'll return. Otherwise, if node of left not equals to null, now one of them is not equals to null, the other one is null. So if node of left is not equals to null, then in that case DFS of node of left will call and with true. Sibling is absent, right? Because if sibling was present, then it would have gone in this code block, right? It would not have come here. So return. If node of right not equals to null, DFS node of right and true. So this should be it. We are passing the additional variable within the DFS, that is sibling absent. If it is true, that is for the current node the sibling is absent. So in that case, we'll add it to the answer. Now we'll go to the left and the right child. We'll DFS on the left and the right child. Now when we go to the left and the right child, we'll check if node of like if the left and the right child have siblings, that is node of left not equals to null and node of right not equals to null, both the child nodes are present. So in that case, we'll call them with false. Otherwise, we'll call them with true. Right. So that's the logic. It's pretty simple. Let's quickly get this done. Compilation completed as expected. Let's run. Okay, we have to output -1 if it is not available. So if answer dot size equals to answer dot pushback -1. So this is done. I hope that you don't have any doubts on this. Pretty simple problem. So let's go to the next problem. Now this is a medium level problem. This is also not very difficult, but again, like it's a good problem. So let's understand this. So the problem statement is you have to do a vertical traversal on a binary tree, right? So today we'll be only solving tree based problems, and the homework that you will have is also based on tree. So today we'll be doing the second problem we'll be doing is vertical traversal of a binary tree, right? So you are given a binary tree, find the vertical traversal of it starting from the leftmost level to the rightmost level. If there are multiple nodes passing through the vertical line, then they should be printed as they appear in level order traversal of the tree. Okay, so you are given this tree. Now vertical traversal means it will be like this, right? First of all, 4, this 4 is going away. After that, second line is 2, so after 4, 2 should come in. Then third line, 1, 5, 6, these 3 are coming in. At fourth line, 3 and 8 are coming in. At fifth line, 7 is coming in. At sixth line, 9 is coming in, right? So this is the vertical traversal of the binary tree. So if you see, this is the order 4, 2, 1, 5, 6, 3, 8, 7, 9. So this is what you have to you have to return in this order. So 1 2 4 5 3 6. Let's understand this again. 1 2 4 5 3 6. 1 4 5. I think it was like this only. Okay, 3 6. 6 was the. Now for this, how will it look like? This will be first level 1. Second level 2 and 5. 2 will be in the second level. 5 and 1 will be in the third level. In the third place. 3 will be in the fourth place. And 6 will be in the fifth place. So it will be like this, that 4. And we are doing from top to bottom in a level order fashion, for if there are same things, right? So it will be after that 2, then 1 5, then 3, then 6. This should be the output, right? This should be the output. Let's actually verify. 4 2 1 5 3 6. It is indeed the output. So how do we solve this? Let's understand the pattern here, right? Let's understand the pattern. So what we are doing here is essentially, let's draw a tree here. So the bigger one maybe. 1 2 5. 1 2 4 5 3 6 3 6 3 6 8 7 9 7 and was it? Okay, let's see. So let's say, let's call this level, like, right, or let's call this level as 0. Level 0. Level means not level order traversal like this, not in this way level will increase, but rather the level will increase and decrease in this way. So if we are moving to the left, we will do level -1. If we are moving to the right, we'll do level +1, right? So now we are moving to the left 2. So 2 will be doing level -1. So level will be -1. Now we are moving to the left side 4. So level -1. So level will be -2. Now we are moving to the right side. So it will be level -1 + 1, that is 0. Now we are moving to the right side. Now we are moving to the right side. What is the level here? To the right side, level is level +1. So 1. We are again moving to the left side. So it will be -1. So 1 - 1, 0. We are again moving to the right side. So level +1, that is 1. For this one, we are moving to the right side. So level +1, that is 2. Level +1, that is 3. So if you see, we have, for every node, we have written down their levels that they are at, and the same level nodes will have the and the nodes that are coming together, or the are getting grouped together, have the same level, right? So see, 4 has a level of -2, which is lowest. After that, -1, only 2 has. After that, for 0, we have 1 5 and 6. For 0, we have 1 5 and 6. So they will be coming in this order only: 1 5 6. For 1, we have 3 and 8. We have 3 and 8. So they will be coming in this order: 3 and 8. For 2, we have 7. For 9, for 3, we have 9. So this is the order in which they should be printed. So basically what we have to do is, now there are multiple ways you can do this. One way is, you can actually start at 0, at level 0, and you can go on going towards minus and plus, as I've done. Now in this case, remember that wherever you are storing, you have to store it against an index of -2 or -1. So probably you will need something similar to a map, because you cannot store it in array, right? If otherwise, what you can do, if you want to store it in an array itself, what you can do is, you can first find what is the maximum to the left we can go. Once you have determined that here we know that we can go maximum to the 2 units to the left, so just mark it at the starting point. So this will become L equals to 2. Start this as L equals to 2 and then make the computation. So everything will be greater than equal to 0, right? So that's the second way, but we'll go with on maps only, right? We'll go with maps only. So for what is the structure of the map? The map will store int. This is the level that it is storing. This will store the level. and vector int, this will be the nodes that it will be storing, right? Now coming from top to bottom, like how they are visited, the way they will be visited is same in DFS as well. Like first our top node, this node will be visited only, then the lower nodes will be visited. So we don't have to worry about that if we are going in a DFS order. Can you repeat once again? Sure. See, is the question clear? Is the question clear? First method without map. I didn't explain actually without map. We have to do. You're talking about the second method, right? So we need to have either an array or a map to store the levels. So what we can do, let me just elaborate on array method without a map. Let's just elaborate on that. So I'll take an example here. Let's say this one, 1 2 4 5, 1 2 4 5 3 6. Let's say it is like this, right? So here, what was the problem? Like, what was the problem if we start at L equals to 0? It would go negative this side, it would go positive on the right side. So we would have to handle for negative values as well. If we don't want to handle that, if we want to store it in an array, what we can do is we can start from a positive L. What will be the value of L? We can try going to the leftmost value. So we see that the maximum we can reach is -2, right? -1 and then -2. Maximum we can reach. So go to the leftmost node, see what is the maximum that you can reach. Start with the positive value of that. That is, we'll start at L equals to 2 here. Now we go to the left, so this will become L equals to 1. Here we go to the right, so it becomes L equals to 2. Here we go left, it becomes L equals to 0. Here we go right, it becomes L equals to 3. Here we go right, it becomes L equals to 4. Now see that everything is greater than 0, right? So what you can maintain here is you can maintain a array of vectors. Vector int ARR, and what you can do here is ARR of level dot pushback node. You can do like this, right? You can do like this, but if it is negative, if we are starting at 0, right? If we are starting at 0, then in that case the issue would be L equals to 0. Here it would become L equals to -1. Here it would become L equals to -2. This would become 0. L equals to 1, L equals to 2. Now if you do ARR of L dot pushback node, here it is -1, right? So you're trying to trying to access -1 index of array, so that will cause problem. Here you are trying to access -2 index of array, so that will cause problem. So ARR in that case will not use a vector of array, rather will use a map or an unordered map, right? So map int vector int will have the definition like this, ARR, and then we'll do the same thing, ARR of level dot pushback node. Do the same thing. So this is also another way. Like these are the two ways. It depends on how you want to implement. Let's go ahead with the map implementation only, because array will be easier. So let's go with the map. So what we'll do here, we will maintain a map to store the levels. So unordered map int vector int level mappings. Now here we'll define a private method. So void DFS int s int node star current and the second variable will be int level, right? So what we'll do, first thing is level mappings of level dot pushback current of node, current of data. First thing that we'll do. Now we will go to the left child. So if current of left not equals to null, then we'll DFS there. So DFS current of left, and level will be level -1. Similarly, if current of right not equals to null, DFS current of right level plus 1, and you're done. So this will be the entire code. Now what you can do here is you can just clear the level mappings. So level mappings dot clear. Then you can run this for run the DFS for root with the level of 0. And then what you can do is you have this mappings, right? You have the mappings. So what now we can do is vector int answer. So we'll traverse from smaller level to larger level only, because in the map it will be stored in that order only. So for auto and v belongs to level mappings, v dot first and v dot second. So answered. So for int node data belongs to v dot second, that is the vector that we have. So we are going in a, so this will go through all the levels one by one, right? So level 0 first will come, then level 1, then level 2. So that will be maintaining that increasing order. Now for each level we have the nodes that are there at that level, so we'll traverse through all of them. V dot second basically is the vector, right? This vector v dot second will be the vector, v dot first will be this that we are at. So node data, and we'll push that to our answer dot push back node data, and finally we can return answer. So this can be the code. And the questions, most of the questions based on trees will be as simple as this, right? They wouldn't be very complicated. Okay, I think it's different. Somehow 7 has come before 715. Huh. How is this treating? Okay, I think what's happening here, level mapping level dot. So can we see out here, see out dot first, and try to check what is happening? Let's try to run. Who's go? Oh, we are actually going in a random fashion. That's fine. Okay, so what we can do here is we can go in an incremental way. So as we are using unordered map, probably it's not sorted. So let's go in an incremental fashion only. So let's maintain a variable here, min level and max level. In min level and max level. So let's set it to min level, int max, and max level to int min. Let's set these things. So min level and max level. So what we can do here is min level equals to min level and min level and level, right? Similarly max level equals to max of max level comma level. So we are just finding the minimum possible level and the maximum possible level. Why is that important? Because we can make a traversal here, min level I less than equal to max level I plus plus. So we are going in an incremental fashion of levels. Now definitely, like, we can get for, so we can have this code under. Let's have this code here. For node data belongs to, where does it belong to? It belongs to level mappings of I. This will give a level mappings of I will give a vector, and we are going in that order. Let's see if that works. 421 output didn't print. Let's see. So see out min level. Oh, we set it after the, we should set this before the DFS. Let's run this. Okay, we are getting it as expected, so let's try to submit this. Five 3 8 5 8 5 3 5 7. Okay, there are differences. 5 9. There must be some differences in between. What are we missing here? Okay, let's take a look once again, like what should be the order in which. So binary tree, if there are multiple nodes passing through the vertical line, they should be printed as they appear in the level order traversal of. So what is level order traversal? Level order traversal is from top to bottom. And how does it go? From first the top node will be visited, after that uh, in level order will go to the left child and then the right child. So the order will be like 1 2 3 4 5 6 7. This is a level order traversal, right? So first the left child should be there, then a right child should come. So definitely a node that at a higher depth. Oh, okay. A node at a higher depth will be coming before, right? That's a problem that we didn't actually think through. Is a node at a higher level will be coming through. So what we should do, instead of DFS, we can just go with BFS, right? Because we just want a BFS order traversal. So let's just go ahead without a DFS. We do void BFS. Void BFS. Let's just do a BFS here, and so let's maintain the Q node star Q, and Q dot push, Q dot push, yes, Q dot push root. So let's pass the root here, node star root, and not only yes, that should be there. Also, let's maintain the level of the no. Maybe we can maintain the level mappings and also maintain the levels, or shall we maintain in the queue itself? We can maintain in the queue itself. So let's make it a pair, right? Node star, and also it will contain the level. So that is the integer. So here we'll push root, not only root but also the level, that is 0. Now while not q dot empty, then what we'll have auto TP equals to q dot front. We'll take the front element. Q dot pop will remove the front element. Now what is the level? So we'll add the level. So level mappings of TP dot first. TP dot first. This will be a pointer to the node TP of first of data. TP dot second, that will be the level. Dot pushback TP dot first of data. The data, right? Corresponding data will push it, and then we'll go to the left and the right child. So if TP dot first of left not equals to null, then we'll go to the left child. Similarly, if TP dot first of right not equals to null, then we'll go to the right child. So what we'll insert here? We'll insert Q dot push TP dot first of left and TP dot second minus 1. The level will be TP dot second minus 1. That is the current level minus 1. TP dot second, TP will contain the top element or the front element of the queue, and then TP, it will contain the node as well as the level of the current node, and will for this node the level will be level minus 1, and for the right node it will be level plus 1, right? So Q dot push TP dot first of right and TP dot second plus 1. that should be it. And also here we can set the min level and max level. So min level equals to min level and tp dot second. Sorry, we can set it outside, right? And max level, max level and tp dot second. I think that should okay, we have called bfs, we should call bfs here. So bfs, I think is it running into infinite loop? No. 42156778. Order should be fine. Let's submit. This is done. So we have basically done bfs instead of dfs, because the way you have to print is only in the level order format. The problem that we faced with dfs was the problem that you will be facing with dfs. Just assume that let's say something like this, right? Let me try to create an example about the problem, like what you will face. So let's say something like this, that 1 2 1 2 3 4, right? And here we have 5. So see, this is level 0, this is level -1, this is level 0, this is level 1 plus 1, this is level 1. So 5 and 4 will both be on the same level, right? But in dfs 4 will be visited first before 5, but we want 5 first before 4, right? So we need to do a bfs, not a dfs. So we can do a bfs and we can store the levels like this. So when we do the bfs in the queue, we are storing both the node and the pair and the int, which is the level. And then to the left child we are giving a level of -1, to the right child we are giving a level of +1. So this is the code. Let me know if any problem, if you have any problem. So I think it's pretty simple as well. So yeah, this is the problem. So as your homework, you'll be solving these problems. Now this is a very simple problem. You have to do level order traversal of the tree, right, of the binary tree. This is the first problem. Second problem is the medium problem. It's a bottom view of the binary tree. Bottom view will be how do you see it from the bottom, right? So 5 10 14 and 25, if you look from the bottom, you can just see these nodes, right? So that will be the bottom view of the tree. Third problem that you'll solve is level order traversal. So I think this is a bit different. Line by line is a bit different. But yeah, just look into this. Like there are two problems. If both of them are same, just solve one of them. So this is basically just have to write the level order traversal code. And the last problem is also a medium problem. It's the sum tree. So you're given a binary tree, return true if every node x in the tree other than the leaves, its value is equal to the sum of the left and the right subtree value. Okay, so it's also pretty simple. So for every node you have to return true if its value, uh, if for all the nodes the sum of its value is equals to the sum of the left subtree plus sum of the right subtree. So that is what you have to do. Okay. So these are the problems for today, and these are the homework. I hope that you don't have any doubts. uh, just make sure to solve them, because these are important. Again, these are very important when it comes from interview point of view. So do make sure that you have solved them. All right, so that's about today. I'll be seeing you on Friday again, and thank you guys for joining me.